What's up, guys? Welcome back to the data structures in Golang series. Last time we did stacks using linked lists and vectors. This time we're going to move on to implementing queues using both of them, both linked lists and vectors. So I'm just going to create two files here. Uh, One would be queue linked, and the other would be a queue vector. Go. So just giving a debrief on what we did last time. Stacks are a structure which basically works in a what we call last in, first out way, where the first item to get into the stack would be the last item to get out of it. And we implemented this structure using a linked list and a vector. And the difference between implementing this using a linked list and a vector is that, well, vectors are a contiguous block of memory. So if we were to allocate this, then all of this would be just one block of memory, one block of contiguous memory, which means that all of these items would be placed side by side, like all in one block. And the advantage of doing that is that random access of any of the items is constant time. If we wanted to access 5 here, then we already have the address of the first item in the list. So we would just add the index that we're trying to access. So since this is the second item in the list, considering that this is 0, then we just add 2 to the address of the first item in the list, and we have our the item that we're looking for. So it's constant time. We don't have to traverse the whole list to access that item. Uh, and on the other hand, the way linked lists work is that we are allocating each node where each node would have a value and the next pointer, and the next pointer would hold the address of the next item in the linked list. And that item could be anywhere in the memory. So basically, the whole linked list is spread all over the memory. We at any given point we don't know where any given uh, like node of the linked list could be. The only way to find that out would be to traverse the whole linked list one node at a time and reaching a given node. So random access of a given node takes a linear time, which means order of n. So we would, in worst case, if we wanted to access this last node, we would end up traversing the whole linked list and coming to this last node. So that's the advantage we have when we use a vector over a linked list. And the trade-off that we have when using a vector and not a linked list is that if we wanted to insert something into a vector at any given random location within the vector, then it would take us n operations in the worst case. And the reason for that is, let's say that this is our vector and we wanted to insert 5 in the middle there. Then since we need to keep this a contiguous block, we would end up we would end up allocating a block of memory here, and we would grab this 4, we would put it here. And then we would grab the 3 and we would put it where 4 was. And now we have a block of memory here where we can insert 5. So basically, we are shifting all of our items by one block in order to allocate memory for 5 in the middle of the vector. So insertion and deletion would take n operations, which would mean we are pushing all of the items after that point by one step, going one at a time. So insertion and deletion could be slightly expensive in the case of a vector, and in the case of a linked list, if this is our linked list, and if this is the element that we want to insert, if this is the node that we want to insert into the linked list, all we need to do is break this chain, and from this node, we just have to create a link there. And from this node, we create a link there. And there. So technically we have created like this that would be how our new linked list would look like. We have broken that chain. We created a link here and a link from 4 to 2. So it took us two operations. So a constant number of operations. And in the case of a vector, it took us a linear number of operations. So that's the trade-off between using a linked list and a vector. With that context given, we can now move on to implementing a queue. So uh, if you guys are not familiar with a queue data structure, it is similar to a stack, but the only difference is that we can we can insert items from one end and delete it from the other end. Basically, how a queue works in real life. If you were to enter a queue somewhere, then if you are the first person to enter the queue, then you would be the first person to exit the queue, which means it's a FIFO or a first in, first out. So that's the basic gist of what uh, what a queue is. Now we can move on to the implementation. And to do that, we can simply copy over everything that we have. So we'll start with the vector implementation of a queue. So we'll just close that off. And now that we have that, we can do the basic stuff where we have a similar slice of integers in our data. We have a max size for our queue that should be that should remain the same way. We'll only de-implement all of these methods. So we don't call inserting pushing in a queue. We just call it enqueuing, and I'm just going to name it envec, and uh, deleting an item is called dequeuing. So I'm just going to call that dvec, and we have a uh, peak vec queue because we already have that implemented in the stack. Let's just start with the insertion. It should be it should exactly be the same as what we were doing earlier, actually. So while pushing, we check the max size. If we have reached the max size, we just say that that the queue is full, and we just exit. If that's not the case, then we just append onto the data that we have, the data slice. And while dequeuing, uh, we we have a similar check where we check if our queue is empty. If it's already empty, then we just say that the queue is empty and we return a negative one. Or else we have a deleted item, which would be, since we're appending, the way append works is that it adds the value at the end of the data. So deletion would be the opposite. So we leave the the zeroth element of our data. That would be the item that we're trying to delete. We'll just return that as well. And right here, we need to delete that item. So the way we can do that is just this. So we're from the first element of the data to the end of the to the last element, we just slice that and assign it to s dot data. Simple enough. And we can do the same thing while peaking, uh, but we just don't delete our last element. So we can just call it peaked and we return peaked. And for testing, we can just initialize our queue by just calling queuevec. Our data would be an empty make with zero items. We would have a max size of 4, and then we can start performing operations there. So we can do q.enqueue. We can have a print statement. So we can just call it. Oh, I just realized I'm doing stack back here. So I'm just going to do a search and replace that real quick. So I'll call it qvec. So we need a q back there. We'll call it print back q. We don't do anything there. And for I is 0, I less than the q dot data dot length. I plus plus. Now we can print like an arrow there, and we can use instead of a print line, we can have a printf for a formatted line, and right there we can have that. Let's see if that makes sense. And we'll need to have a print line here where we just print an empty arrow. Let's see. So I'm just thinking of the formatting there. Is it gonna look like a cube? I think it will. So let's try to print the cube right now, and we'll have to have this as the max size. I'll need to call this from the main function. Okay, awesome. So we have enqueued one item. Now we can try it with multiple items. Cool. So we see that as soon as it hits four elements, we say that the queue is full, and we don't append anything to the queue, and we can just get rid of that space there just so it looks better. Awesome. So now we can start. Now we can try to peek something, and whatever we peek, let's try to print that. So format print line, uh, peaked, and then we can start doing the dvec without print, and we just do that a bunch of times again while uh, while the queue has any items. So we peaked 1, 2, 3, 4. If we see that we also deleted it. Did we? Okay, yeah, we didn't because I'm not doing a print line here. I'm sorry, a print vec. Yeah, so as soon as we do the print vec, we see that we did not delete it, and now we start to delete elements from our queue. So we got rid of 1, 2, 3, 4, which was our first item there, which was the first item that got into the queue. That's the first item that got out. And then 2, 3, 4. So this looks good. So this was our vector-based queue. Now we can move on to our linked list-based queue. And the way to do that would also be pretty similar. We would copy over the code from our stack because, as you might have observed, a lot of this stuff is pretty similar to what we had in our stack. We can just rename this to queue linked. Now, this is the different part. Instead of using a singly linked list like we did in our stack, we can rather use a doubly linked list, which we also implemented in our series. And the reason to do that would be we're keeping track of the head and the tail in the doubly linked list. And the benefit of doing that is if we wanted to push from one end and if we wanted to enqueue from one end and dequeue from another end, if we used a singly linked list, we would have to traverse the whole linked list and then we would reach the end of the linked list and then we can delete that element. And if we were to use a doubly linked list, we would directly have access to our tail. So that's the benefit of using a doubly linked list there. So let's just use a doubly linked list and we will implement this from the beginning, all of these functions. So pushing to a linked list. We are not pushing anymore. We are enqueuing. So n linked, d linked, peak linked queue, and print linked queue. And we don't need to have that. Instead, we will have a queue linked. All right. And we can also get rid of those S's there and just call them queue. So It's it's more consistent. So to enqueue, I think we can just do insert start, and that should be enough. Insert start doubly, we just pass in the value. To delink, we can do a delete end doubly because we're inserting from the start, we're deleting from the end. That's how a queue is supposed to be. Peaking, we, oh yeah, I forgot about checking our the size of the linked list to keep track of the max length and so on. So to do that, we would need to make our length public in our W linked list. So let's just make all of the elements public. So the values needs to be public, the length needs to be public, the head, the tail, and I think that should be enough. So we check the length if it's equal to the max length, q dot max length, then we do what we did here. We just print and we return. And similarly for the queue is empty, uh, we check for the length. If it is equal to 0, then we'll need to do data.length. If that's equal to 0, then we just print that the queue is empty and we return. Or else we'll need to get the item which is at the end. And by end here, we mean the tail. So we need to have tail.value. This is our deleted item, and we return the deleted item. Awesome. So peak would also be similar. We just don't delete. And printing, we just do a q dot data dot print doubly backwards because that's the way we were doing over here. Uh, so in this case, the head would be here and the tail would be here, so we're printing backwards. So that's why we're using that function. And now we can start testing our linked list based queue. And the way to do that would be create a new W linked list. Uh, Now we'll need to create uh, a queue linked with the data as linked list new W linked list where we pass in nil and the max length would be 4. Now we can perform our operation. So n linked 1, 2, 3, 4 q dot print linked q, and we can just repeat these. We need to call it from our main test q linked. Okay, you see that 1, 2, 3, 4 has been enqueued, and this, then this, then this. Makes sense. Now let's try to dequeue from our, or we can try to peak first. So peak would just be that. We would do a format print line peak. Even though peak is technically the same operations that we are doing in delete, so we don't really need to have this for our case, but because we have implemented it, let's just utilize it. Print, do this a bunch of times until it's underflown. And we see that we peaked here. Let's just print it one more time after we print peaked. Uh, yeah, so we peaked 1, 2, 3, 4. We did not delete it. Now we start to delete. We deleted 1, 2, 3, 4. Then this. So the first item that got inserted was the first to get deleted. Awesome. So in this video, we implemented a queue data structure using both vectors and linked lists. I hope you learned something from this. Thanks for watching. I'll see you in the next video.